Well, where we left off last time was around binary search, right? But we basically, we know what the trick was, right? If I told you to pick a number between 1 and 1024, my trick was to always guess the middle. So I'd guess 512. And the reason I would guess 512 is you're either going to say higher or lower. Because the data is sorted, that's the trick. The data for binary search must be sorted in order for it to work. I have to be able to go, where do I continue the search? If I had an unsorted list and I guessed the thing in the middle of that list, and the data is not sorted in any way, there's no way for me to know if I'm looking for X and I'm looking at 17, I have no way of knowing is X guaranteed to be to the right or to the left because it's not sorted. I have no way of knowing. But with binary search, if the data is sorted, I guess right in the middle. And you're going to say higher or lower. If you say higher, I know the data is on the right side. Like I know to keep looking between 512 and 1024. If you say lower, I know to keep looking between 1 and 512. Really 1 and 511 because I already guessed 512. No matter what, I get to throw away half of the data. And there's no way I can do better than that unless I'm guessing that I'm hoping the data is higher. I can never throw away more than 50% without risking throwing away less than 50%, right? If I guessed 256, maybe I'll get lucky and you say lower, and then I've eliminated 700 and whatever, and I only need to keep looking at like 255 things, right? Maybe I get lucky, but I might get unlucky, and you might say higher, and I go, shit, all right. So throwing away half of the stuff is pretty good. That's as best we can do where we guarantee, like that's the optimal way to do it. With linear search, think about this for a second. And I believe we talked about this last time, but this is just hitting what we hit last time. If I have a list of size n, and I look at the first thing, and I say, is this what I'm looking for? Let's say I say no. How many pieces of data did I eliminate from my search? Only one. Only the one thing I looked at. I look at another thing. I eliminate one thing. Another thing. Another one thing I get to eliminate. But with binary search, it's different. Every time I make a guess, I'm going to throw away half of the stuff. And that's why it's better. Because every guess I make, I can make a huge conclusion. I can conclude 512. You say lower, I go, great. I've now eliminated 512 things from my search. That's amazing. I'd make another guess, 256. You say lower. Okay, I've eliminated another 256 things from my search. That's amazing. So that's why binary search is better. But of course, with linear search, I ask the question, what's the worst case scenario? If I have a list of size n, how many things do I have to look at to guarantee I find that thing? Tell me. Wake up, come on. N, of course, it's n. But how many things do I have to look at? If you give me a list of size n, and I say it's sorted and you can do a binary search, how many things do you have to look at? N over 2? No. You're close-ish. Every guess I make, I eliminate half the things. What's that special operator we use if we are dividing repeatedly? Pardon? No, that's if we want to do integer division. I'm thinking more just think of math. Throw away programming for a second. Think of math. Look, if I let's take a moment and think about the basics of arithmetic. The simplest thing I can do is count, right? The simplest thing I can do is increment by 1. That is the simplest thing I can do. So if I told you, and don't overthink this really is a simple question. But I want to be clear, it's simple, and I'm not saying it simple to trivialize it. I'm saying it's simple because I know you can answer this. And don't think I'm being like, what's the word I'm looking for? Facetious, I think is the word I'm looking for by asking you this. No, I want you to answer this question. If I told you increment by 1 10 times, right? Let's say I gave you 5 and I said increment by 1 10 times. What do you do? You count from 5 to 15. So you got to 15. So we go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? But then you say to me, well, that's kind of silly. You don't count by 1 10 times. What would you do instead? You just add 10, right? So addition is like this generalization of counting. When I say plus 10, it means increment by 1 10 times, right? I'm not being silly. That's, basics of arithmetic there. Probably haven't really thought about it like this because you don't really teach 3-year-olds it that way, but that's what it is. So if I say, okay, I want you to, we've generalized counting. We have counting now. Or sorry, we have addition now. And if I say, I want you to add 10 times, do you go, okay, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, right? That's adding 10 times. But of course, you say to me, well, that's just what? Multiplication, right? So multiplication is like doing addition multiple times, right? Would you agree with that? So let's say I have 10, and I said, well, I want you to multiply 10 times. And you go, okay, well, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is... Let's pick an easier number, because it's going to get too big. Let's say it's 2. If I say multiply 2 5 times, I go, okay, well, 2 times 1 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? So 2 times 2 times 2 times 2. So I'm multiplying multiple times. But what happens, what do you say that is? What operator is that? Actually, yeah, like to the power, right? So like, that's just, yeah, great. 2 to the power of 5. No, 2 to the power of 5. Yeah, there we go, right? So that's like doing multiplication multiple times. So we started with incrementing, and then we got to addition, then we got to multiplication, and then we got to the power, right? But of course, what's the opposite of incrementing by 1? What's the opposite of adding 1? Thank you. What's the opposite of like just addition? Yeah. What's the opposite of multiplication? What's the opposite of to the power of? Square root? Think of like exponents, right? What's the opposite of like the exponents? Square root only works for like squaring, right? Log. Yeah, log. So if I said like 2 to the power of 5, it's 32. But if I wanted to do log base 2 of that, why did it do that? Well, that's just 5. So like the log base 2 is the inverse of doing 2 to the power of. You should know this. This is like high school stuff, right? You learned logarithms in high school, right? Okay, I'm seeing nods. You better have. Either that or high school's really gone to hell. Holy moly. So 2 to the power of 5 means multiplying by 2 every time. But when we were doing binary search, we weren't multiplying by 2 every time. What were we doing? Yeah, we were dividing. We were eliminating half of the stuff every time we did it. So if I had 1024 things, and I want to do log base 2 of that, well, that's 10. And you remember what I said last time? I said pick a number between 1 and 1024, and I'll guess it in 10 guesses, or less. It's because by eliminating half of the stuff every time, I'm dividing the amount of things I have to look at by 2 every time. The total amount of work I have to do is log base 2. Almost all, if logarithms scare you, don't worry. They scare every computer scientist too, except for log base 2, because log base 2 is easy. It just means keep dividing by 2. I can do that. That I'm happy with. So log base 2, usually computer scientists, when they say log of something, they always mean log base 2. So often you won't see the base 2 mentioned just because everyone knows it's log base 2. What's the default log, though, in general in like mathematics? What base? 10. 10, yeah, very good. But computer scientists were like, screw that, we like 2. Right? We're obsessed with 2 in computer science. So log base 2. So with binary search, the amount of work I need to do isn't linear based on the input size. It's logarithmic based on the input size. If you give me an input size of n, and I'm doing linear search, the amount of work I have to do is n. And if I double the size, how much more work do I have to do? 2n, double the amount of work. But with binary search, if I gave you an input size of size n, the total amount of work you have to do is log base 2 of n. If I doubled the input size, how much more work do I have to do? Yeah, but you could actually give me a more precise answer. One more unit of work, because I'm just dividing by 2 every time. So if I double it, well, I'll just divide it by 2 one more time. $11. You double the input size, I only had to do one more thing of work. If you have an algorithm to solve a problem that's linear, and the person next to you has one that's logarithmic, you should feel really bad about yourself. If you have a logarithmic algorithm to solve a problem, that's amazing. We want that. It's so much better than linear. Linear is not that bad, don't get me wrong. But if you can have something that's log, way better. Way better. Because think of the amount of work. If I gave you 2048, a list of size 2048, and you had to do a linear search, how many things do you have to look at to guarantee you found it? 2048. If I gave it to you and said do a binary search on it, how many units of work do you have to do? 11. If I gave you a list of size 1.125 times 10 to the 15, that is huge. No. Here, something times 10 to the 30, okay? That number is that number's hilariously big, okay? That is huge. That's probably like how many in Milky Way. All right, our galaxy, So to put it into perspective, it looks like our galaxy has times 10 to the 67 particles in it, right? Now, obviously, this number is not nearly that big. But let's see. There. We're getting close to that. Let's make it like 250. There. 2 to the power of 250 is some number times 10 to the 75. That's bigger than the number of particles, atomic particles in our galaxy. All right? And I told you do a linear search on it. And I say how many things you're going to have to look at. You're going to say, well, 1.8092514 times 10 to the 75. It's going to take a while, isn't it? But if I told you to do a binary search, how many things do you have to look at? 250. 250 is nothing. Nothing. Times 10 to the 2. It's nothing. Binary search, I'm showing you this to give you an idea of how much better binary search is. Linear search is garbage compared to binary search. But what's the catch? Can you always do binary search? No. Your data must be sorted in order to actually do binary search. If it's sorted, you're good to go. If not, you're screwed. You got to do binaries, or you got to do linear search. Any questions about that? Yeah. Okay, cool. So, any last questions before I move on to the next little thing? Now, last time, I believe it was last time, we were talking just a little bit about 162, right? Just a little prep of it. Now, one thing programmers tend to be a little worried about did I show you this last time? I don't think so. Okay, good. I may have shown some of you this in lab. One thing the new programmers in 161 get a little weirded out about when going to 162 is they get a little worked up about the fact that they're switching programming languages to Java. And I get that. I get why you're concerned. But trust me, it's actually not that bad. There's a bit of a jump, don't get me wrong. You got to figure out that transition. You got to do it. But most students, when they enter 162, for the first week, they're kind of freaked out by it. And then after that, they realize, oh, wait, no, he was right. It's nothing. Because the algorithms are the same. The code that you're looking at, like the algorithm, linear search is the same in Java as it is in Python. The difference is syntax. Don't get me wrong. There's a syntactic difference, but there's no semantic difference. The algorithm is the same. So here's an example of a linear search in Python. In fact, I could have made this even better by adding type hints and whatnot, but I didn't. But here's a linear search in Python, okay? What does it start with? Well, def linear search, haystack, needle, and then we've got a for loop that's going to go from like 0 to the length of the list, -1. And then I look at the thing in the haystack. If the thing at index 0 is needle, I'm done. If not, I look at the next one. Haystack at index 1, is it needle if I'm, So what do I have? I've got my function definition. I've got my loop to loop over all the things. And I've got my if to check if each thing's the thing I'm looking for. If I ever find it, return true. If I ever get to the end and never find it, I return false. Linear search. Think of the pieces of the algorithm. This doesn't need to be in the function definition. This doesn't need to be in a function. I put it in a function because I like to label things. So I've got linear search. It starts with the function definition. I've got my parameters. I've got my for loop to look at each thing. I use my if to check each thing. If it's true, return true. If I ever get to the end, return false. That's the pieces. Function definition, loop, if, and my returns. That's it. Any questions? That should be pretty clear. So here it is in Java. And your first thought is going to be, wow, yeah, that does look different. But it's not. There's syntax there. You're seeing public static, what is Boolean, what? But that first line is just the function definition. And of course, other languages, I didn't add the type hints to the Python one, maybe I should have. Other languages don't use type hints, you actually just have to say the type. But this is saying, well, I've got haystack, which is like this means an array of integers. You can think of it like a list. I've got a list of integers, and I've got an integer. That's what the parameters are there. And then we see a for loop. And yeah, the syntax is different, but all that for loop means is go from 0 to the length of the list, minus 1. If haystack at I equals needle, return true. If I ever get to the end of that loop, return false. The algorithm is the same. I've got my function definition with parameters. I've got my loop to loop over each thing in the list. I have my if to check each thing, and if it's true, I return true. If I ever finish that loop, I return false. The algorithm is the same. Sure, the syntax is different, but the algorithm is the same. The difference in the if is, okay, we have parentheses. In Python we use white space for to mean things are inside of the function and the loop and the if. In Java, we use these squiggly brackets. They're called braces. That's what we use. Every statement has to end in a semicolon, whatever. But these are just some syntactic differences. That's it. If you know what you want to do for a linear search, but you don't know how to do it in some language, if you know I need a for loop in Java, not JavaScript, then you can find the syntax. If you know the algorithm, you can find the syntax later. No one's going to expect you to memorize the syntax like that. I expect you to know what a for loop is. I expect you to know what an if is. I expect you to know how to make a function. How you do that in any given language, you can figure that out later. It's the syntax that's you just figure it out. Knowing what to do, knowing the algorithm is different. The syntax and the algorithm are different. That first line, though, public, remember how I said, remember with Python I say if you start a thing with underscore, it means leave it alone? In other languages, if we had something like that, we would use the word private in front of it. If it's not private, typically it's public. So we have to be explicit in these other languages about everything. It's visibility. Static, don't worry too much about that one right now. It basically means it's a function, whatever. Boolean. Anyone want to guess what the Boolean means here? I know you don't know, but I'm willing to bet you could guess. It returns a Boolean. This function returns a Boolean. You need to tell, just like if I had a type hint here, I'd have that little arrow bool. Same idea. This function returns a Boolean. Name. In Java, we use camel case. That's camel case, not snake case. Snake case is the underscore. Camel case is each new word starts with an uppercase except the first word. Unless it's a class, then it starts with an uppercase, but not that important. An integer array, think of it as a list. This for loop, it just means, okay, I've got this counter I, it's an integer. It starts at 0. It goes to I less than the length of the haystack. This is how I get the length of that array. Instead of len, name of my list, I say name of my list.len. But again, it's an array, not a list. And then each time through the loop, this means, anyone want to guess what plus plus means? We haven't seen it in Python. It doesn't exist in Python. Add 1. It's the same thing as plus equals 1, or I equals I plus 1. It's an even shorter shorthand. Your for loops, when you're using range, you can specify all three things. By default, all you need to specify is the length, and by default it starts at 0, but you can change what it starts at. You could also change by what it counts by with range as well. It's the same shit here. Just syntax is a little different. Your if, you need parentheses. And here's the big one. The Boolean starts with a lowercase. In Python, it starts with an uppercase. Ooh. But the algorithm is the same. I hope you see my point that the algorithm is the same. A lot of time new programmers get worried about changing languages because they think, well, it's going to be different. But how different is it really? How different are programming languages from one another? You know, I can go look at, what is the list? List of top. I don't want that one. I want this one. Let's look at the top programming languages right now. Most popular. We got Python, C, C++, Java, C#, JavaScript, PHP, Visual Basic. I could include JavaScript, but let's look at these right here. The top 5 programming languages. Okay? Let's see how similar they are. Well, I showed you Python versus Java. Look at Java versus C#. I'm going to try to get them both on one page. Can you see any differences? How different are those languages? Can you see any differences? Because I hope not. They're literally identical. Java to C#, in this particular example with the linear search, the syntax is identical. If the syntax is identical, obviously the algorithm is the same. Yeah. They're a different color? Yeah, and same with the length. Oh, you got me. There's a different color of the text. They're the same. A lot of these popular programming languages, all of those popular programming languages there, at least in the top 5, top 6, their syntax is basically, if you're looking at this, you're like, yeah, the syntax is different. An experienced programmer will look at this and be like, not really. The syntax is actually really not that different. Obviously it is. To a new programmer, this feels a little bigger. And obviously it's more different than Java to C#, which is literally the same. But now let's look at C++. Here's C++. Okay, instead of an array of integers, I use something called a vector, fine. And instead of like haystack.length, I say haystack.size, and it's a method because it's got, the parentheses. Other than that, it's basically the same. I don't have public static. I could put public in front of it most of the time. It'd be fine. But it's basically the same. Very, 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 very similar. And here's C. The biggest difference with C is I've got an array of integers. But in C, this isn't quite true, but for the most part, the way we do in this example, arrays don't know how big they are in C. Like, you know how I can ask a list how big it is? Think in C, like a list doesn't know how big it is. We have to remember that. So we create another variable here called like n to know, well, that's just the length of the haystack. So I don't loop to the length of the haystack, I loop to n because that is the length of the haystack. So you can see, look at this, 5 languages. Python's the weirdest one, actually, but it's really not different. Python, Java, they're all function definition, loop over each thing, check each thing, return true, otherwise return false at the end if we finish the loop without returning anything. It's the same. Here's something that's different. Does that look different? It should look different. When programmers say, oh, that language is, it's quite different, they mean more like this. I'm just giving you context for what different means. Here, the syntax is obviously very different. And the algorithm is different. It's really not that different, actually, but it is different. Raise your hand if I showed you this in lab before, because I know I showed this to a couple of people in lab before. Okay, 2 people remember it, 3 people. Can anyone make sense of what this means? It's actually not that bad. And actually, a lot of programmers look at this code and like, if I could see through the syntax, and the syntax really isn't that bad, but this algorithm, especially with the syntax, this algorithm is actually like, to a lot of programmers, like this is like aesthetically beautiful. And I know it sounds weird, but it's true. There's like a beauty to this algorithm right here. I'll start by explaining the first line. The first line really is just the function definition, okay? That's really all it is. We're creating a function called linear search. It's an equation on something of type A. Now, when I say type A, think of A as a variable for a type. It doesn't matter what type it is. I just have something of some type A. And that function takes a list of type A and a single thing of type A and returns a Boolean. So if you give me a list of integers and an integer, I'm going to give you a Boolean. If you give me a list of strings and a string, I'm going to give you a Boolean. That's like what the type A means there. So that first line is just that function definition. The next line is what I did at the end of that last class. And let's do it again just for fun. Who's going to be the volunteer? You're probably going to remember it from the end of last class, so that the trick is already spoiled. But I need a volunteer. Was anyone here not at lecture yesterday or 2 days ago, whenever it was? No one here right now wasn't here on Monday? Really? All right. Well, I was going to use you as a guinea pig. The way to know, I'll say it again, you're going to be my volunteer. I know you know what I'm going to do. If you forget, good. I'm going to give you a list of 1 billion things. And I'm going to get you to tell me if something that I'm looking for is in that list. Actually, no, I lied. Let me start over. I'm going to give you some list of whatever, okay? And you're going to have to tell me if the thing I'm looking for is in that list or not. That's your job. But the catch is, I'm not going to tell you what I'm looking for. But you still need to tell me if it exists in there or not. And I've got good news for you. You can answer it, which sounds weird. I'm going to tell him to find something in a list, but I'm not going to tell him what I'm looking for, but he's still going to be able to tell me if that thing's in that list or not. Raise your hand if that sounds kind of weird. Yeah, well, here it is. Here's the list. It's empty. Is the thing I'm looking for in that list? No. I know it's not there. Which sounds stupid, almost kind of like, well, yeah, no shit. But there's actually, it's actually a clever observation. So what this first line here means says, look, if you ever give me an empty list, that's what that syntax means. If you give me an empty list as my list, and the underscore means, and I don't give a shit what else. Literally anything, I don't care. The answer's false. If you give me an empty list and you're looking for, I don't know, it's not there. The thing you're looking for is not in the empty list. Right? Right. That's what that first line here means. Now, the next line has 2 parts to it. This right here is an OR. It's a special OR. It means like short circuit OR, which means short circuit OR means, okay, I'm going to ask you a question. Am I wearing a shirt, or do I need to even ask you the second part of that question? What's the answer? Exactly. So a short circuit OR means like, look, if this is ever true, you're done. If it's false, well, okay, then we actually have to go check out the other side. There's a similar thing with AND. Am I wearing a hat and you know it's false. I'm not wearing a hat. If the first thing's false with AND, it's false. Sometimes it is important to evaluate both sides, so you have a way to do it otherwise. Typically, you do the short circuit, though. It's faster. But this line has 2 parts. The first part here says, okay, this syntax means any list can be broken down into two parts. The head of the list, which is the thing at the very beginning, and everything else, right? So if I have some list A, B, C, D, that means give me A, and then I also have like B, C, D, like that. Okay, that's what that means. All right? That's all that syntax means. Now, you also have a Y. So this says, I've got a list, I take the head, I've got the tail, and I've got Y. If X equals Y, if A is the thing I'm looking for, what does A equal Y return if it is what I'm looking for? It's true. So this whole thing returns true. I found what I'm looking for. But let's say I didn't find what I'm looking for. Let's say A, which is X in this scenario, the value of A and Y are not the same. What do? Well, that's easy. I just do a linear search on the tail of the list for Y. Take a moment and think about what I just said. There's a function called linear search. Where is the function linear search defined? Well, it's not just the first line, it's those 3 lines of code. Those 3 lines of code are the definition of that function linear search. So this is kind of weird, right? The function linear search, in its definition, makes a call to the function linear search. Which is weird, right? We've got a function calling itself. Let's just follow this through. I know this sounds weird, but it's actually, I'm not throwing you anything new that you don't already know. So let's just do this. I see a function called linear search. What does that mean? All right, well, I've got the tail of the list. Let's go back here. So I'm doing a linear search on this list here, B, C, D. I get the head of that list. Well, that's B, and then I have C, D. Is B the thing I'm looking for? If it is, I'm done. If not, what do? Oh, just call a linear search on the remainder of that list. Well, that's just CD. So now I have the list CD. I take the head out of that, and I say, is C the thing I'm looking for? If it is, I'm done. If not, I just call a linear search again on the remainder of that list, which is just D. Is D the thing? Oh, actually, no, I got to get the head out of that list. If I take the head out of the list, what am I left with? What's the tail? An empty list. Yeah, there's nothing left there, right? If I take D out of that list, the remainder of that list is nothing. So is D the thing I'm looking for? If it is, I'm done. If not, call linear search on the remainder. All right, so the remaining list is this. I see an empty list. What does that mean? It's not there. Return false. That's how this works. So obviously the syntax is different. Obviously the algorithm's a little different, but really, is it? We looked at each thing and checked if it was the thing I'm looking for. If it was, I return true. If not, I return false. I'm going to write this function the way it's written here, but in Python. Okay. Oh. I'm going to make it very verbose, just for the sake of being verbose. Let's test this real quick. Pardon? Yes, you're absolutely right. Should have done that first. If haystack. And you know what? We could actually make this more similar. No, I'll leave it like this, and then I'll change it slightly to make it even more similar to the Haskell one. Let's start by testing if it's 0. True. Let's look for like 3. True. Check the last thing. True. 8. False. Yeah. Looks pretty good. And we can be very explicit and do this. False. So this is that like same algorithm written in Python. But here's what I'm going to do. I'm going to make this more similar. Return or there. Or let me do it this way. Make it even more similar to the Haskell one. Because Haskell, half of it's just the fancy syntax. There. It's pretty good. There. Now the syntax is even more similar to the Haskell one. So this algorithm is different, but is it really? This looks at each thing one at a time, checks if something's equal, checks if the current thing is equal. If it is, I'm done. If not, keep looping. But of course, there's no for loop here. But yet this algorithm can loop. It can iterate. And the way it iterated was by calling the function again. Let's take a moment and look at an example here, just real quick here. If I say def, what will this code do? Well, one step at a time. I call it with 0. So look at that function. I've got, n is 0. What does line 2 say? Print out 0. And then I call the function again with n plus 1. Well, what's 0 plus 1? 1. Great. So I call the function with the argument 1. So let's go to the function All right, what is n right now? 1. What do I print out? Great. Now I call well, what's n plus 1 now? 2. I call with 2, the argument 2. So I just go to the function All right, what's n right now? It's 2. It's 2. When I hit run, what's it going to do? An infinite loop. Almost. It'll break because I didn't add a colon. That's not what I meant. Yeah, it just counts. It prints out every number from 0 up to, but then it eventually actually crashes. But it is looping. And if it wasn't for some restriction by the computer, it would be an infinite loop. The fact that this doesn't loop forever is actually a consequence of how these computers work. This right here, we see something called a recursion error. Maximum recursion depth exceeded while calling a Python object. Blah, 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 blah. Great. This error, or an exception, goes by another name in other programming languages. It's got a more common name. Does anyone know what the more common name is? I don't expect you to, but I'm curious if you do. Stack overflow. This is a Stack Overflow error. So that's where the name Stack Overflow comes from, is a Stack Overflow error. And by the nature of how recursion is done on these computers, on how these computers are designed, there is a reason there's a limit on how many recursive calls your code can make. So if it goes too deep, the programming language or the computer will be like, okay, you're done. Now, that's not because recursion intrinsically has to have some stopping. No, it's just because of how these computers work. But recursion is not, anything you do with recursion, you can do with a loop. Anything you do with a loop, you can do with recursion. That's a matter of fact. You can't. In Haskell, there's no such thing as a for loop or a while loop. If you want a loop, it's got to be recursion. It's got to be recursive. Sometimes new programmers see recursion and they go like, well, you just did a more complex way of looping. But I didn't. It's not more complex. It's different. The only reason it's throwing you off is because you have had 2 months of doing a loops with for loops and while loops. If I started you programming in a language like Lisp where you would use recursion, and I showed you a for loop, you'd be like, well, that's weird. It's like recursion, but in a weird way. Yeah. It's just different. In fact, one of these two things, recursion, is a far more natural way of iterative things, of iterative processes that exist within our universe. Anything in nature that has like some iterative constructive process, it's done by building off of itself. It's done recursively. There's no for loop in how ice crystals form in those patterns. It's just based on the current crystal structure and it keeps building on top of it. It's recursive. That's how you get those interesting patterns. Any of these iterative processes that happen in nature are recursive. There's no for loop. There's no while loop. This is far more natural. You got a question?
I had a question and then I thought of it and I thought of a way to actually.
You can, but you gotta be careful doing that. You absolutely can, but that's a recipe for a headache. So going back, someone asked in the other section, okay, like is recursion a faster way of looping? No. In fact, recursion is actually slower on these computers. Now, in terms of what it means mathematically, one is not faster or slower than the other. That's really not something that makes sense. But by the nature of how these work, recursion is slower, only because of how these work. Someone could design a computer where it isn't slower. They could, they just, we do it that way. But something that's interesting is a lot of common popular programming languages, Java included, you could write code that's recursive, and when you compile it to run, Java will leave the code recursive, but it'll actually convert it, like when it turns it into the zeros and ones that get run, it'll actually change it as if it was written in a loop because it's faster on these computers. Because writing things recursively is sometimes a lot nicer than writing things with a loop, and vice versa. But we'll pick up here next time.